Hi guys, when we left off in class last Thursday, we had discussed ionic and covalent bonds. And we finished up talking about covalent bonds and how they are directional and therefore very strong. So they occur where the electron suborbital clouds overlap with one another in neighboring atoms, and the neighboring atoms share those overlapping electrons. So yeah, directional, very strong bonds tend to form crystals with low symmetry and high hardness, things like quartz or diamond. Let's move on to discussing now our last valence-related type of bond, and that is metallic bonds. Let me shrink this down. There we go. Okay, metallic bonds form when many atoms get very close to one another, and all of those atoms collectively share the same electrons, which are free to move through the crystal structure. So this is different than, say, one carbon atom getting together with exactly 4 other carbon atoms in a structural arrangement such that each carbon atom is sharing 4 valence electrons with a neighboring set of carbon atoms. In this case, what we have are a bunch of what are usually transition metals that get together in the closest packing arrangement that they can find. And then their electron clouds essentially become a kind of mobile glue. And the electrons are free to move throughout the pore spaces or the intervening spaces between the nuclei of all of these atoms. Like I said, most metallic bonds form when transition metals get together. So those would be the orange colored elements on the periodic table here that are in that central block of the periodic table. So transition metals are defined as being those that have valence electrons in the really large D and F suborbitals. A perfect example of this might be the mineral native copper. Native copper and other native minerals like native gold, native silver, native lead, native platinum. These are all elements where you have a close packing arrangement of transition metal atoms that get as close together as they possibly can, and their electron clouds around each one of the gray gumballs with a plus sign if you're looking at the image in the top part of your screen. So they all get together and arrange themselves close to one another. And then their electron orbitals become kind of like a shared large cloud. And electrons then, that are again loosely held in these really large D and F suborbitals, are able to move throughout the structure between and around all of those positively charged metallic nuclei. When this occurs, you tend to develop solids that are incredibly dense. They tend to have very high specific gravity. They tend to also have metallic luster, so they will be opaque, and instead of allowing for any light to be transmitted, instead all of the light that hits one of these native metals or a mineral that is dominated by metallic bonds will be reflected back, such that they will appear to have these shiny metal-like surfaces. So again, they tend to have metallic luster, they tend to have pretty low to moderate hardness, and importantly, they are very good thermal and electrical conductors. And that shouldn't be any surprise at all because the electrons are free to move throughout their structures, meaning that charge can physically be carried or conducted from one part of the solid to another. For the same reasons, metallically bonded solids tend to be very malleable, meaning that if you were to hit a metallically bonded solid, it wouldn't be brittle and break like an ionic solid would. Rather, it would deform malleably. So imagine like a strip of copper wire. If you were to put your hands on the edges of the strip and kind of bend them down, the wire would bend instead of snapping. That's what it means to be malleable. So metallically bonded solids are actually pretty special. They have physical properties that are quite different than the physical properties of minerals that are dominated by ionic or covalent bonds. I warned you at the beginning of lecture last Thursday that we're going to talk about these three types of bonds, but as it turns out, most minerals are not 100% ionic, covalent, or metallic. So I've given you some really classic examples of end members like halite in the case of ionically bonded solids, or diamond in the case of covalently bonded solids, or native copper would be a great example of something that is nearly 100% dominated by metallic bonds. If we look at the chart on the bottom, what this chart is showing is the difference in electronegativity across the horizontal axis by the percent ionic character in the vertical axis. And something that's interesting here to note is that even halite, which is our idealized ionic solid, only really achieves a ionic character of about 78-79%, meaning that it's not even 100% ionic. There is some sharing of electrons in a covalent style, even in the structure of halite. So across the x-axis, I told you, is the difference in electronegativity. And if you recall, chlorine is highly electronegative, and sodium has a very, very low electronegativity. So the difference between the two of those is something like let's see, what would that be? 2.4, something like that. Turns out that the difference in electronegativity between sodium and fluorine is even greater. So that tells us that fluorine probably has even higher electronegativity than chlorine does. And even though NaF is not a mineral, if that were a naturally occurring crystalline solid in the earth, it would be nearly 100% ionic. It would approach, what is that, maybe 93-94%. So something to keep in mind when we think about all of the major rock-forming minerals, most of them are going to occur on a sliding scale between covalent and ionic. So plotted onto this ternary or triangle diagram are the minerals olivine and amphibole. And as you'll see, they plot somewhere along that sliding scale. Amphibole is kind of in the middle, olivine leaning a little more ionic. Most of the silicates, though, the minerals of greatest interest to us in Earth's crust, are somewhere between mostly covalent and mostly ionic. Okay, so just to recap, we've discussed now the three different kinds of valence-related bonds: ionic, covalent, metallic. Of the three, covalent are the strongest, followed by ionic. Metallic bonds are relatively weak compared to the other two types. So they will the materials made with metallic bonds will be malleable and they will flex, but they can be bent and they can be scratched, which is why they have relatively low hardness. There are a couple of types of bonds, however, that do not involve valence electrons. Those include van der Waals and hydrogen bonds. These are very, very, very weak bonds, so weaker yet than even metallic bonds. Okay, and they occur because some nuclides or some atoms in mineral structures have residual weak charges to them, kind of in the same way that we talked about a molecule of water having some net residual charges around the positively charged hydrogens or the negatively charged oxygen, simply because of the asymmetry of the molecule. So the same is true in some atoms based on the way electrons kind of spin in their suborbitals. You can have some kind of net lingering weak negative or positive forces occurring around those atoms. And in some cases, they might be just strong enough to hold, for example, sheets of carbon together in the mineral graphite. So graphite is a polymorph of diamond. Let me see if I can get my Apple Pencil to work here. Let's see. Polymorph. So polymorph, poly means multiple and morph means shape. So graphite and diamond are polymorphs of one another. They both have identical chemical compositions. They're both made only of the element carbon, But whereas the carbon atoms in diamond are 100% covalently bonded to one another in all three dimensions throughout the entire structure, in graphite, those carbon atoms are only bonded together in sheets. So the picture in the lower right shows carbon atoms that are bonded together to make these super strong covalently bonded sheets. But those sheets are only held to one another through van der Waals bonds, and those are very easy to break. So every time you put a pencil to a piece of paper, you are breaking van der Waals bonds in the mineral graphite, and you are leaving behind on your piece of paper tiny little flakes of carbon, of strongly bonded carbon. So yeah, graphite makes up pencils, and the reason why pencils work the way they do is because graphite is an incredibly weak mineral of low hardness, and it doesn't take anything at all to break those van der Waals bonds. Having said that, it would be very difficult to break the sheets themselves because those are covalently bonded carbon. They'd be hard to break. Let me move this to the side to make it a little easier to see. There's also something called hydrogen bonds, and these are the things that hold minerals. Hang on one. These are the things that hold sheet silicates, platy minerals like clays together. So this is very similar to the graphite structure, but in this case we have part ionic, part covalently bonded silicate sheets. So all of the little purple pyramids that you see in the picture on the bottom, those are silica tetrahedra. We're going to talk about those a bunch. And they are strongly bonded to aluminum octahedra. Those are the polygons that are blue and teal. So those are very strongly held together in these sheet-like structures, but the sheets themselves are only very weakly bonded to one another through these hydrogen bonds. And therefore, kaolinite, like graphite, tends to break along these planar features very easily. And for that reason, kaolinite and other clays tend to be very small. So mineral crystals tend to be very small, and they tend to have a very, very distinctive plate-like structure. So the image in the lower right is a really, really zoomed in, I think it's a 52 times magnification view of crystals of kaolinite taken with a scanning electron microscope. And you can see that really distinctive kind of flat, platy structure that these crystals develop, thanks to the tightly held, covalently and ionically bonded silicate parts of the structure and the very weak hydrogen bonds that hold the sheets together. So we've talked about how most elements in the periodic table are reactive because they don't have their outermost electron shells completely filled like the noble gases do. And that's what they're striving for. So they're going to react with one another in order to achieve that full electron configuration. And when I say they react with one another, what I mean is that they're going to form bonds with one another. They're going to physically come close to one another so that they can either give and get bonds and develop oppositely charged nuclei, which will then be electrostatically held in the case of ionic bonds, or maybe they will get close enough together that they can physically share electrons along a directional axis, like in the case of covalent bonds. Or maybe their strategy in the case of transition metals with these really large, high energy, loosely held valence electrons in d and f suborbitals, maybe they'll all get together and pack in as tight as possible and share their valence electrons through this like electron glue of metallic bonds. Regardless of how they do it, the point is these elements are very reactive and when possible will tend to bond with other atoms to form compounds. So in addition to thinking about positively or negatively charged ions, we can think about these things as existing as radicals or complexes, molecular complexes with net negative charges. Some examples include what happens when silicon and oxygen, carbon and oxygen, nitrogen and oxygen, sulfur and oxygen, or phosphorus and oxygen get together. You'll notice that oxygen is the is the oxidizing or the negatively charged part of all of these radicals. And that should come as no surprise given that oxygen is the most abundant element in the mantle and the crust of the earth by quite a lot. And it's also very, very highly electronegative. So it is abundant, it's everywhere, and it's eager to form these bonds and to create these radicals. So when a silicon cation becomes oxidized or gives up electrons in order to bond with oxygen, it will give up 4 of those electrons always. And so it will get together with 4 oxygen atoms to create a radical with a net negative charge of 4 minus. When carbon does this, carbon will get together with 3 oxygen anions to form the carbonate radical, which will have a net negative charge of 2 minus. Sulfur will create the sulfate radical, which will have a net negative charge of 2 minus, and phosphorus will do this to create a net negative charge of 3 minus. We're going to talk about these radicals a lot, especially the silicate radical, because it's the building block of all silicate minerals. But for now, I just want you to understand that these radicals are really the foundations of most mineral structures that we're going to think about in this class. Okay, that's it. Thanks for listening.